Um, all right. Hello, everyone. My name is Michał Dulko. I am a software engineer working in the OpenShift and OpenStack team at Red Hat. And you might remember me as the Courier guy, right? So Courier was using Octavia a lot. And when we started to validate the integration between Octavia and cloud provider OpenStack and OpenShift, our QE, when they had a problem with Octavia, they came to me. So I will present the findings that we had and the workarounds that we figured out. And in general, I will tell you what works and what doesn't in the Kubernetes and Octavia integration. So I will focus on the type load balancer services and not and I will talk a little bit more about MetalLB later on, but don't expect too much about this. But I will not talk about the Octavia ingress controller. That's part of cloud provider OpenStack as well, but we don't use that in OpenShift. In OpenShift, we have a different component doing ingress. So I don't have much experience with this. I will not talk about the capo or the cluster API provider OpenStack integration. They use the Octavia to create a load balancer for the API, Kubernetes API. That's a tiny bit of integration, but that won't be part of this presentation either. So let's jump straight in. And that's one clarification I need to make. So a while ago, the cloud providers were implemented in the Kubernetes tree, like the main, because they were part of a kube controller manager. And soon they realized that was a bad idea, but the entry cloud provider stayed, and they are pretty easy to use because they are part of the kube controller manager. You don't need to deploy a separate service cloud controller manager. So you might be tempted to use them. Please don't. So the entry provider, the OpenStack entry provider, is removed in Kubernetes 1.26, meaning that very soon there will be no supported Kubernetes version that still has the entry provider. And the entry provider was implemented for the Neutron LBAS, not Octavia. The Octavia support was added like this, so they basically replace the endpoint if you tell the cloud provider to use the Octavia. So the calls remain the same. This is possible because the LBAS API, the Neutron LBAS API, was the same as the basic version of the Octavia API. And this means that we are missing features that Octavia provides. And I've highlighted two most important ones, the fully populated load balancer creation and the healthmonitors support. And later on, you will understand why these are critical for the Kubernetes and Octavia integration. So let's talk a bit about Octavia. And I think the main problem with the integration with Octavia is that it's not a perfect abstraction layer. Behavior of the load balancer depends on which backend you choose, and the backends are called providers in Octavia, and I know cloud provider OpenStack, cluster API provider OpenStack, and providers here. Well, it's confusing, I know. So the main and the default reference implementation of the Octavia provider is the Amphora. And in Amphora case, the load balancers are VMs spawned on Nova. This means that they are slower to create. They use more resources because each VM needs some RAM and vCPU. And interestingly, as a design choice, they have no source IP preservation. It's like the traffic is NATed, and the traffic coming to the member is having the IP of the load balancer and not the real source IP. You can work this around using the HTTP header injection or the proxy protocol. That's a feature that Amphora is supporting. And it has a lot more features like the L7 rules and so on, but that's not really related to the cloud provider OpenStack. On the other hand, you have the Oven Octavia provider. That's kind of a secondary implementation. Michael will tell you that it's not part of Octavia, right? And it is using the underlying Neutron instance to implement the load balancers. And this means that you need the Neutron to be configured with Oven. That's one requirement to use it. It's great because it's fast to configure and doesn't use the much resources because it's implemented on the SDN layer. It has the source IP preservation, which is cool, but later on you will learn that it's it has downsides as well. And in the cloud provider OpenStack context, it has some functional gaps, like Amphora simply offers more options. Below, I've highlighted code needed to be put into the configuration of the cloud provider OpenStack in order to configure the Oven provider to be used. So LB provider equals Oven, that's an obvious one. But LB method needs to be set to source IP port because that's the only load balancing algorithm that the Oven Octavia provider is supporting at the moment. So yeah, we also, to understand this presentation, we need to understand how the load balancer services work on the Kubernetes side. And this is the very simple case. We have a setup for the service A. So cloud provider OpenStack had created a load balancer A, and each of the nodes of the Kubernetes cluster is added as a member of that load balancer. And Kubernetes had have chosen a node port for each of the for the service, right? And this node port is allocated on each of the nodes. And this node port is not really a port in Neutron or something. It's just a port chosen from a range, like a port number. Then Kubernetes will make sure, it's kube proxy in most cases, to redirect the traffic that is coming into the node port into the pod of the service A in our case. Now, an important thing is that each node is added as a member of the load balancer. It doesn't matter if it has the pod of the service or not. And this strikes a scalability question. Like, what happens if you have 100 nodes in your Kubernetes cluster? Well, Octavia is pretty much fine with that. But if you had the old in-tree cloud provider, which doesn't have access to the features of Octavia, you needed to add the members of the load balancer one by one. And each time you add a new member to the load balancer, load balancer will become pending update, and you need to wait for it to become active again. Meaning that if you have high number of nodes, it can take, I don't know, up to an hour to add all of the members. That's not really acceptable, right? So you really want to have the fully populated creation. That's something that the modern cloud provider has, the CCM-based one. So let's talk about how the traffic works in these cases. And this is the most simple one. So load balancer, the traffic comes to load balancer, right? The load balancer chooses a node, and it happens to be a node that actually has a pod of the service A. So the traffic is directed into the node port, and then it's redirected into the pod. That works perfectly, right? It can also happen that the traffic will go into the node that doesn't have the pod of the service. In that case, if you have the basic default external traffic policy equals cluster case, then this traffic will be redirected into the node that actually has the pod of the service A. Now, this is the default because it's a conscious decision by the Kubernetes developers in order to enable better traffic spread, because you can have multiple pods of a service in a single node, and then you want this node to be targeted more often. But this may cause another hop to a node, so kind of a delay here. But also we lose the source IP, and the service A doesn't, the pod of the service A doesn't have the real source IP of the client. And you can opt out of this and use the external traffic policy, set it to local on the service. It's all set on the Kubernetes service. And then there are no redirections. So if the traffic is hitting a node that doesn't have the pod of the service A, it's lost. It's dropped. It should be dropped. That's an interesting case. So why would you want to do this? Well, technically, you have the source IP preservation. So if your application needs that, you can have this. There are no additional hops, so technically it might be a bit faster, but it will be worse at spreading traffic, especially if you have multiple pods on a single node. So how do we deal with the case when the traffic is directed to the node port, to the node that doesn't hold the pod of the service? Well, if you set the external traffic policy to local, Kubernetes will also assign another node port called health check node port to each of the nodes. Well, it's a single node, port number, but each of the nodes has it. And on that port, an endpoint, HTTP endpoint, will be available, telling you if the node holds a pod of the service or not. So now we can deploy a health monitor that will hit the health check node port, and then for the node 1, the endpoint actually will say that, hey, there are no pods, that's a failure. So the health monitor will disable the node number 1, and this way the traffic will always go to the nodes that hold the pod of the service A. So cool, right? So this way we can have the source IP on the pods, right? Well, not really, because as I told you, the Amphora does not preserve source IP, at least by default. So cloud provider OpenStack allows you to use 2 features of Amphora. It's done through the annotations. You set these annotations on the service. And the first one is loadbalancer.openstack.org/x-forwarded-4. And that enables the HTTP header injection with the source IP. And the other option is to use the proxy protocol that also allows you to read the source IP. So I've told you that Amphora does not preserve source IP, but Octavia does. The only problem is that only recently it got the health monitors support, and without health monitors, we cannot really use external policy set to local. So yeah, you need a fairly new OpenStack for that. And this is something that I've grabbed directly from the code. It's like mapping between the OpenStack versions and the version of the Octavia API. And these are not micro versions. You cannot request a previous version. These are you can read the available API versions, and then you can deduct which features are available or not. Later on, I will show you a table with the features there. So let's talk about incompatibilities between versions. And well, Health Monitors API has, so I told you that Health Monitors came only in Wallaby. And in order to check for that, do not check the Octavia API version. So Wallaby, let's say that's 2.24. But do not check the Octavia API version, because Octavia provider is a separate repository, separate Python plugin. It's possible that your cloud administrator installed a different version. So it's better to just call the API and see if it will be not implemented error or not. Another problem is that, as I've told you, the endpoint on the health check node port is an HTTP endpoint. And interestingly, Amphora does not support HTTP monitors on the UDP pools until API version 2.16, right? That's usually release. And Oven does not support HTTP monitors at all. So in order to work around this, we've implemented a fallback in the cloud provider OpenStack. So it will fall back to the TCP or UDP connect monitors, but hitting the node ports, not the health check node ports. And that's because health check node ports is an HTTP endpoint. So for the TCP health monitor, it's always okay, right? So it needs to monitor the node ports. And now that there's an interesting consequence. So the UDP connect monitor is relying on the ICMP message only emitted when the connection is rejected and not dropped. Now, Kubernetes documentation requires the CNI or the kube proxy to actually drop the connection and not reject. I know that Oven Kubernetes does reject against the specification, so it works in that case. But with kube proxy, you won't be able to do the UDP connect monitor, so that simply won't work with Oven. And yeah, that's a tiny problem that was highlighted by the folks raising issues upstream. So the members of the load balancer are on by default. That's a conscious decision of the Octavia developers. But if you add a new node to the cluster, then until the health check will say that, hey, this node is actually not holding the pod of a service, some traffic might be directed to that new node and be lost. So there are other load balancer options that are kind of implemented, but that depends on the backend you use in Octavia. So session affinity in Kubernetes, you can only set the client IP here. So the session is based on the IP of the client, and that's implemented using the session persistence on the pool set to source IP. That only works with Amphora, and we've realized that it's kind of implementable in Oven with some restrictions. So currently there's a patch in review that implements this for the Oven Octavia provider. But yeah, at the moment it only works with Amphora. There are two more options, like the annotations that you can set on all the services, and the connection limit and all the timeouts. And I think the Oven does not implement this as well. That's something that I've realized only today, so I haven't been able to check completely. I've only looked in the code, but I think this is missing as well. So Amphora is supporting this, but not Oven Octavia provider. Load balancer source ranges, that's the way to restrict the accessibility of the load balancer so that you can set just a number of CIDRs that will be allowed to actually call the load balancer. And with Amphora, that works using the allowed CIDRs set on listeners. That's supported since the train release, but yeah, it only works in Amphora. And this is an interesting case because on Oven, you need to manage this through the members security groups. So Oven folks are refusing to implement the allowed CIDRs API because it kind of doesn't make sense with Oven where the source IP is preserved, right? So you can set on the members of the load balancer, you can set a security group, and you can filter the IPs because you will have the exact client IP there. So manage security groups option in the cloud provider will do that. It doesn't do so at the moment. Let's talk about this option then. So this is a refined version of one of the first diagrams that actually shows that this traffic from the load balancer into the node actually needs to go to the security group. So somehow you need to open the node ports there. And if you don't have dynamic SG management, you need to open the node port, full node port range. That's quite a number of ports. And in case of Amphora, as it is nothing the traffic, you only need to open it on the nodes subnet because the load balancers are running on the nodes subnet. So the same subnet as the Kubernetes nodes. But for Oven, as the source IP is preserved, well, you need to open it for the whole world, or if you expect the client IPs to be from some range, you can restrict to that. But that's a bit scary, right? So there is an option in the cloud provider OpenStack called Manage Security Groups. And with that option, the cloud provider OpenStack will create an SG for each of the load balancer services. It will only open required ports, the node ports for that service. There can be multiple ones. And it will also open the health check node port as well, because it has to be reachable as well. And then it attaches the security group to each of the nodes. And yeah, that's solving it, right? Well, that doesn't really work with Oven at the moment. It only opens the nodes range, so it's designed for Amphora. And yeah, with the Oven, we need to open a broader range. But it's an option to implement the load balancer source ranges so that if we take into account the load balancer source ranges, we can filter based on that option on the security group of the members. So this is something I'm working on at the moment in the cloud provider OpenStack. And I've told you, I will tell you a tiny bit about MetalLB. So a colleague of mine had recently, so if you need these links, I know that QR codes would work better. At the bottom, there's a link to the slides. It's dulek.github.io/Kubernetes-Octavia. And yeah, highly recommend that. So this is how to deploy the MetalLB on OpenStack with the BGP option, BGP mode. And yeah, the MetalLB has its own issues. So L2 mode doesn't really load balance. You need to rely on Kubernetes doing the rebalancing then, because mode will only hit one node at a given time. And PGP mode is breaking any connectivity on the members list change, so any ongoing connections will be broken. Moreover, and this is highlighted in the frequently asked questions of the MetalLB, the MetalLB is spoofing the source IP addresses. So there is a mechanism, anti-spoofing mechanism called allowed address pairs in OpenStack, and this will block MetalLB from working. And you have a bunch of options. You can disable port security, but that also disables the security groups as well. So that's scary. You can try to implement a controller that is setting the allowed address pairs dynamically. That should be doable. But the MetalLB folks are refusing to add this into the MetalLB, by the way. And the problem with this is that the API to add allowed address pairs is not great. I think it improves in the Bobcat release of OpenStack. They have an extension to atomically add or remove a single pair of the addresses. So yeah, it's doable. And another idea we had is to use a secondary port, like make MetalLB use a secondary port attached to each of the nodes, and then we firewall that port differently, like maybe using the IP tables on the node itself. So let's go into the summary. I will repeat again, don't use the entry cloud provider. It's a bad idea. With Amphora, you have the high resource consumption because of each of the load balancers is a VM, but it has great Kubernetes compatibility. And even in the very limited context of the cloud provider OpenStack, it has richer feature base. Some of the stuff, it might be implementable in Oven as well, but it's not at the moment, and this is something that may only come in the future. With Oven Octavia, yeah, low resource consumption, it's very fast to start a load balancer. But with the Kubernetes compatibility, it's like in progress, I think. And I would say that the main issue is around the safe security group management, so that you don't need to open a whole bunch of ports for whole the world. There are some issues with the UDP services. In general, if you plan to use the UDP services with load balancer type, I would recommend to double check everything, because this is where the devil is, right? So with MetalLB, as I've told you, it has its own issues, limitations, and maybe it's an option if you don't have Octavia in the environment, but honestly, I would probably recommend going with Amphora if you have Octavia available. So this is a tiny compatibility matrix. I've only shown the versions starting from train, but then I've been to a presentation today that was showing that someone is using Queens still. So I've realized that I need to extend this. So yeah, in Rocky, UDP service in Amphora, that's cool. The UDP support came in Stein in Oven, and I think they've extended that a little bit in train. Yeah, mixing UDP and TCP services is only possible in Oven from train. Then yeah, load balancer source rangers for Amphora, UDP services monitoring in Usuri, and SCTP protocol, that's pretty cool, I think, and Wallaby is having the most broad feature base at the moment, I think. And soon, this Oven should get the limited support for the session affinity. And I'm working on the improvements to manage security groups option. So it needs some fixes, like being able to delete the security group rules, actually. And I think SG security groups are not applied to new nodes. That's something that needs to be added as well. And then this work might result in support for load balancer source ranges for the Oven. So I'm just a developer working with the QE team. So I don't run Kubernetes on OpenStack, but I think you do. And there might be a lot more corner cases and problems that you've encountered. So tomorrow, with Matt, we held a session about Kubernetes and OpenStack. We want to hear from you about the problems you have, the architectural challenges, the workarounds that you have in the environment. So it's tomorrow at 2:30 There's an Etherpad. You can add questions there, and it's an hour and a half, so we'll have a lot of time to discuss anything you would like about the OpenStack and Kubernetes integration. So yeah, and the code lives on GitHub. As you can see, it's a separate repository now. It's not the Kubernetes one. And if you want to reach us after the summit, we are in the Provider OpenStack channel on the Kubernetes Slack. And yeah, that's it. And it seems like I still have some minutes to take question, right? And so if you have questions, please use the microphone. And yeah. All right.